Right, so in this video we'll be talking about ionic bonding and right, so ionic bonding. The main idea being that atoms become ions by either donating or accepting electrons. And what happens when ions come together? So you have, let's say, ion 1, ion 2, and that they want to bond with each other. In that sort of situation, you have ionic bonding. And here we'll try to make a rough model of that. So take for an example, you have two ions with a positively charged nucleus and electrons flowing around everywhere on the outside shells. Let's call this distance, which is small r, and remember this is also referred as interatomic separation. So what we're saying is that this is atom 1, this is atom 2, and the separation between these two atoms is the interatomic separation equal to r, right? So two major forces that play a role here are attractive forces and repulsive forces. And the attractive forces can be given or written by F subscript A, repulsive by F subscript R, and therefore you can get the F net as FA plus FR, a total summation of net forces on your system, right? So let's try to look at the attractive force first. Attractive forces between ions, something that is given by a commonly known law, the Coulomb's law of attraction. And the force Fa here will be given by constant, let's just write it as a constant for now, multiplied by Q1 multiplied by Q2 divided by R squared. And again, remember here R is the separation and Q1, Q2 are the charges on the individual ions. And that constant can vary depending on what units you are writing. So let's just call it K for now. You can find that constant in a question or in the book anywhere, and that will just depend on the units that you use. And then keep in mind that whatever units are used for the K, also keep a constant unit for R. So the R can be sometimes given in nanometer or angstroms, sometimes even in meters. So just be mindful that your constant has the units that can work accordingly. Now this was the attractive forces. The repulsive forces that we'll be dealing with. So let's draw the repulsive forces. Repulsive forces, which is given by Fr. Very simplistically speaking, that will be equal to a constant divided by radius to the power n. Again, here B is constant, that will be given to you in situations. R again is the separation, and then n is your order of repulsion, and that will also be given to you. And as and when you learn more about these topics, you will try to understand how to get the value of n by yourself. So using this system, what you can have, or let's try to plot a curve to see how will this look like. So I'm gonna make this line, and then let's have this one over here, this one over here, this one over here. and then I will try to have the energy curve in the same plot. Right, so the top one will be our force curve and the bottom one will be the energy curve. X-axis is small r in both situations, and always remember a relation between the force and energy is that dE over dr equals to F, or you could write it also in this expression, E equals to integral of F dot dr, integrating from infinity to r. Very, very important relation. Always remember that this works in any system. This is a general definition. So using that and the equation that we just wrote, again, so remember we have attractive, repulsive and net forces that we need to draw. So let's start with the attractive forces. If you remember, this has a relationship of r square, right? So because we're drawing F versus r, your attractive forces will have a slope of 1 over r square, and that will go something like this. Let's draw it with a dotted system. Dot, dot, dot. And this will be your attractive force, which you can also write as F subscript A. Now let's look at the repulsive force. Because it is repulsive in nature, that will be the opposite sign, and what that can be given as is something like this. Because it is 1 over r to the power n, it will have a much steeper slope, and you could also consider the repulsive force after some distance go to 0. So if you want to see, this is the 0, this is plus, this is minus, and then again this is your repulsive forces, or FR. And then when you add these, what you will get at the end is a curve which somewhat looks like this. And this is your net force. This blue line is your force net. One thing you'll notice is that the point where force net is 0, let's highlight that out and extend it down. This distance is referred as R0, where R0 is the point where F net becomes 0, and this is also referred as the equilibrium separation. And this is the point where there is no net force acting on your two ions. It is a net zero system, therefore it is the most stable point. And your atoms or ions can sit absolutely stably at this distance with each other. At the same distance, because it is the most stable point, it should have the least energy, right? Because it's the most stable. And if you remember, the expression that we wrote for energy is equal to F net, or E equals to integral of F dot dr. When force is 0, when your net force is 0, your differential or the slope of energy will also be 0. So if you now draw the attractive and repulsive forces, what you will find, let's draw those again. So this will vary as 1 over r this is your attractive energy, and the repulsive energy will look almost the opposite. And similarly, your net curve will look something like this. So let's draw the net energy curve, and keep in mind the point where you have R naught, you'll have a minimum energy situation. So what you'll have is something like this, and this blue, and again this slope here, this is the dE over dr equals to 0, so you have R naught, and then this value is given by E naught. And again, just to clarify, the blue is E net, or the energy of your system, right? So an important point to note here: at equilibrium, very crucial to remember these ideas or these points. The first thing is that at equilibrium, your R is referred as R naught, which is also called as the equilibrium separation. Second, your F net is equal to FA plus FR. Now that is everywhere, but at equilibrium this becomes to 0, which gives you FA equals to minus FR, right? And the third point, energy at equilibrium is referred as E naught, and if you remember the fourth point, dE over dr, which was F net, is just equal to 0, because again from this point your F net is 0. And this is how you can solve any problem with these four conditions. So let's do a quick example solving these problems. So in this system, you have been given the ionic radius of Mg2 plus and F negative ion. So this is 0.072, this is 0.133 nanometers. Calculate the force of attraction and the force of repulsion. So force of attraction formula is given over here in this form, and here again Z1 and Z2 refer to the charges, the Q1 and Q2. And if you see this modulus outside, and that is just to avoid any sign confusion. So if you just plug in your values over here, 2.31 into 10 to the power minus 28 into 2 into 2, this will be 1, into 1 divided by your R naught square. Here the R naught would just be equal to R Mg2 plus R F minus, because what we're doing is we are considering hard sphere models. So if you have Mg plus, so let's say this is Mg2 plus and this is your F minus, what we're saying is that the distance between them is my R naught. So it is basically the sum of this radius plus the sum of other radius, and then you can write that over here. So if you write it in the numerical form, that will just come down to 0.205 into 10 to the power minus 9 whole square, and then you can solve this to get a numeric value. And for the force of repulsion, if you again remember what we studied just now, that at equilibrium Fa equals to minus Fr. So you can take that system and just write it out. So at equilibrium F net equals to 0, therefore Fa plus Fr equals to 0, therefore Fa equals to minus Fr. So whatever you calculate from this situation, this Fa, just the negative of that will give you the force of repulsion. Why? Again, because we are at the equilibrium interatomic separation. Alright, and you can do the math for this and calculate it. Let's quickly look at the next question. This is a bit math intensive, but again, if you remember that one equation that I talked about, that's all you need. And the equation is dE over dr would be 0 at equilibrium, right? So what you have been given is that you have been given the net potential energy between two ions. You have to calculate the equilibrium interatomic spacing and then calculate the equilibrium potential energy. So with this expression, you can write En equals to minus A over R plus B over R to the power N. And again, here N is the order which is given to you. 9, A constant is given to you, and B constant is given to you. So let's keep the constant in their constant form and do the differentiation of this. This will become A over R square. This will be minus B times N times R to the power N plus 1. Right? And then we need to have this equals to 0, because this is equal to 0 at equilibrium, because the net force is equal to 0. And now what you need to do is, and then if you make this 0, your R will be equal to R naught. So you can write this in this format: R naught square minus Bn R naught to the power N plus 1, and this should be equal to 0. So if you solve this, this will be looking something like this: R to the power N minus 1 equals to Bn divided by A. R naught, so your R naught would just be Bn divided by A whole to the power of 1 over N minus 1, and then your B is given to you as 5.86 into 10 to the power minus 6, and your N is given to you as 9, and then A is given as 1.436, and then this goes over 1 over N minus 1, and N is 9, so we can write this as 1 over 8, and this will be your R naught. And from here, because you know R naught, you also know that E equals to E naught at equilibrium. Therefore, you can take that expression of En, A minus A over R plus B over R to the power N, and then at equilibrium, you know that En would just be minus A over R naught plus B over R naught to the power N, which will be equal to E naught. And here you just calculated the R naught value, so you can plug that in here. You know A, you know B, and you know N. So this will give you the value of E naught equals to something. And again, remember, E naught is at equilibrium. And this is how you can solve this example question. And again, for the part C, all you have to do is just plug in these values into the general expression you found: A, B, and N. So this was a discussion on what is ionic bonding looking like, how are the attractive forces, the Coulomb's law of attraction, the repulsive forces, how to draw the plots of energy and force, and what happens at equilibrium. I would say this is a very crucial and very important part of this entire discussion. So keep a note of this if you can. Thank you.